class. Now we are going to discuss second application, that is Venturi bit. Venturi bit. Venturi bit. What is the Venturi bit? Actually, it is a device to measure the flow of the fluid in the pipes. We can measure, okay, how much quantity of fluid is moving. So we can find the rate of flow of fluid in the pipes by using this Venturi meter. We can measure it. Okay, actually, this is Venturi meter is contains a unique cross section of two tubes. Okay, this is one unique cross section of the tube which has area cross section. I'm taking this is a same unique cross section of the area. Okay, so this is a unique cross section area of the tube. This tube is connected to one more a narrow tube of a unique cross section. This is a small narrow. Okay, this is like as a small narrow of a unique cross section area. Okay, that means here this one has a unique cross section. This is a narrow cross section of another tube. Okay, now. So this area cross section taken as here as A1 right here. Okay, this also taken as A1 only. This area cross section of this tube is taken as here and back as A2. Okay, both are same only. Okay, this one. Okay, consider this one. Now this is connected to another tube of U shape. There is a tube which is a U shape. Okay, it is a U shape. This is the Venturi meter. Okay, now we can go next to discuss here. So in this Venturi meter, in this tube, there is a fluid. There is a contained mercury. Okay, and right here mercury. Initially, the mercury is in these two limbs is silver or mercury, whatever it is, the fluid contained. Okay, in these two limbs, the mercury level is initially at a same level, there is no differences in the mercury level. Okay, both are same level. Now here I am taking here in this. Okay, a fluid is right here. Fluid means you can take an area. Okay, which is flowing horizontally. Actually, Venturi meter is works on the principle of Bernoullis principle only, but the fluid is flowing horizontally. Okay, so actually Bernoullis principle is GH1 plus half V1 square plus P1 by rho, which is equal to this is GH2 plus half V2 square plus this is taking P2 by rho. Okay, so Bernoullis principle is applicable to when it is so different cross sections of the tube. There is at different heights. You see here height is H1, this height is H2. For this case, different. This is applicable. Okay, in this case, which is applicable. But now I am taking here. So this Bernoullis principle is I am taking for which case here I am considering here for horizontal flow. For horizontal flow, this Bernoullis principle we can recognize how it is written. So this Bernoullis principle is height is the difference is level is 0. Height is 0 only. So the base half I am taking V1 square plus I am taking P1 by rho, which is equal to half I am taking as V2 square plus I am taking as P2 by I am taking as rho. This is application for a fluid is flowing in horizontally. Okay, this is the equation. A fluid is flowing horizontally, then it can apply Bernoullis principle. This is the equation. So here Venturi meter is okay, which is works on the law Bernoullis principle. The fluid is flowing horizontally. That means here the fluid is entering the tube with velocity v1. Okay, that means I am considering either constraint here or any other fluid also. Here I am taking as different fluids. Okay, I am taking mercury. Here I am taking as iron. Okay, this is enter in the tube. Iron is enter in the tube. Here area of cross section is more. more, A1. Here velocity is less. Area is more according to equation of continuity. Area is more, velocity is here less. When this liquid or fluid or air which is entered into a narrow tube of area of cross section A2, this is a narrow tube of area of cross section is A2, then what's happening here? Yeah, the area is here less, then what's happening corresponding velocity is here increase. That velocity break has V2. So it is coming to with great velocity, So which is area of cross section is A1 more, velocity is less. At this case, the fluid is entered through area of cross section small, then which is entered the great large amount of the speed. That means your speed is higher, more. Then what's happening here? When the pressure is velocity is increased, at this point pressure is less. At this point pressure is less. Then here this is pressure is inside, pressure is more, velocity is less. So here pressure is here less. There is pressure is less here. Here at this case pressure is more, and at this case pressure is more because velocity is less. Then this liquid in this tube, U-shaped tube, that is rises because there is a variation in the pressure. Okay, here pressure is less. Here pressure is more. There is a pressure difference between in this and in this both. Then what's happening? The liquid level in this tube that is a little bit that is rises. Little bit that is rises. Little bit that is rises. This is liquid I'm taking as height is I'm taking as H. I'm taking H. Then some of the liquid that is entered up. Some of the liquid that is a small drop that is entered. Then the fluid is coming out. So we can apply here Bernoullis principle. What is the speed? What speed that is entered? What speed which is entered here? We can find out this speed. We can find out here. Okay. So applying the Bernoullis principle here. We can apply the Bernoullis principle here. So listen here. First I'm taking as half. I'm taking as V1 square. Plus the pressure is I'm taking as atmosphere, I'm taking as here P1 by taking as rho, which is equal to I'm taking half, I'm taking as V2 square plus I'm taking as P2 by taking as rho. Okay. So Bernoullis principle, this is for hydrogen fluid. So half V1 square. The fluid is entered in this tube with speed V1, which means which has kinetic energy. And which is pressure energy, which is pressure. Okay, at this end the pressure is taken as P1. Okay, so pressure is taken as here P1. So per unit mass. Okay, and which at this narrow end, okay, which is entering this speed is taken as V2. This is here kinetic energy is taken as half rho v square. V2 square. At this end, the pressure is taken as which is less, that is taken as P2. At this end, the pressure is taken as P1. Okay. So here pressure is taken as P2. Okay. So this is the energy. So corresponding here, I'm taking half rho V1 square plus I'm taking as P1 by I'm taking as rho, which is equal to half I'm taking as rho V2 square plus I'm taking P2 by rho. So P2 by because I can take it here. So both cancel here. Then what's coming here? I take both sides here. I'm taking P1 minus P2, which is equal to half rho V2 square minus half rho I'm taking as V1 square. This is the equation which is coming here. So according to equation of continuity, so here A1 V1 equal to A2 and that is V2. So find V2 equal to A1 V1 by and that is A1 V1 by that is A2. Okay. This V2 value we can substitute in this equation. In this equation we can substitute. The replies are that here P1 minus P2 equal to half rho into V2 value. V2 is how much from here? A1 V1 by that as A2 whole square minus half I'm taking rho V1 square. So that is equal to I'm taking half rho V1 square I'm taking common. What coming here? a1 by a2, this is a whole square minus 1, this is coming. Okay, this is a p1 minus, I'm taking as a p2. Keep this equation 1. This I'm taking as a equation 1 outside. I'm keeping equation 1 outside. Okay, now we are going to discussing one more equation. So here, when the fluid is passing through this narrow area of cross-section A2, its velocity is large. Pressure is less. Okay. Here, pressure is more than this pressure is applied as at this end applied the pressure applied as P1. Due to pressure difference at this top of the fluid, at this there is a difference is there. The difference applied as P1 minus applied in P2, which is equal to which is a rising some amount of fluid, so which is potential energy here. Okay, potential energy of the fluid applied as rho. That means I'm taking mercury, density of the mercury I'm taking as rho m, and then G into angular gravity and G into H. H means I'm taking a difference in this two units. Okay, 2 units I'm taking here. So this equation I'm taking as 2. So from equation 1 and from equation 2, we can calculate here. Okay, what coming here? So I'm taking rho m into I'm taking GH, which is equal to half rho V1 square into this is the A1 by A2, and then has a whole square minus 1. This is the equation. So find this velocity V1. So from that you can find out here 2 into rho m GH. Okay, by and that has a rho. This equation y this side, this is coming to like this: A2 by A1 whole square minus 1. There is a v square. This is the equation. Okay. This equation you can find out here. So this is the equation v square. So we can find out v1 value, v value. Okay. That implies v is I'm taking as this is v1. No? So v1 equal to 2 into rho m GH by rho into this is A2 by A1 whole square minus 1 whole power, this is 1 by 2. This is the velocity. This velocity V1, which is entered into this tube. Okay, this is the Venturi principle. With one velocity which is entered into the tube. So this is the velocity. Okay, you can find out this velocity.